So, after a short 6 months, we're back. I do apologize that I stopped making videos. I was finishing up college and, lots of things are happening at the end of college. So, I'm finally settled into my new job and I have a little bit of time, so let's jump back into it. So today we're going to be going over some numerical methods, which are ways to approximate solutions to rather difficult, complex functions that would be hard to solve analytically. So the first of these methods is going to be Newton's method, which you can find on page 60 of the FE reference handbook that I have linked in the description if you want to take a look at that. So our first example is going to be use Newton's method to find the root of the following function. So we got a function f of x equals x cubed minus 8 with an initial x of 1. So to start off with this, we look in the handbook and we see what the formula is for Newton's method. I'm going to write it in a slightly different way because that's the way I learned it. In essence, it's exactly the same. So x of k plus 1 equals x of k minus f of x of k minus f prime of xk. So there's our formula for Newton's method. So as we can see, the denominator here has f prime of x, so why don't we just go ahead and solve for f prime of x very simply. So f prime of x is going to be 3x squared, so we'll be using that in our formula. So now we have everything to just go ahead and start iterating. So x1 is going to be 1 minus f of 1 over f prime of 1, which is going to be 1 minus 1 cubed minus 8 over 3 times 1 squared, which is going to give us 3.33. So now we got x1, we can keep going and get x2 and just keep iterating. So we take 3.33 and then we plug it into our x2 equation. We'll do that. Minus f of 3.33 this time over f prime of 3.33, which will give us 2.462. So now I'm going to set up a table that'll kind of help us organize the important things that we need to know. So we got xk plus 1, our error, and m to mean our how many significant digits we have correct. So with our first x, we had 1, which gave us 3.33. So to find our error, we're going to take our new value of x minus our old over our new times 100%, which will give us about 70%. So that means, let me move this m a little bit. That means we have no significant digits correct. So we already solved for x2, which was we take this, bring it on down here, 3.33, which gave us 2.462. Let me actually move this down one. So then if we solve for the error the same way we did before, we get about 35% this time. But again, that is 0 sig figs correct. So using the same method of iterating and going through, on the FE, you're likely not going to have to iterate a ton of times because you have about 3 minutes per question. So doing all this iteration, likely not going to happen, but if they were to give you a question that you need to use a numerical method, and you know Newton's method right off the top of your head and you just want to go for it, just go for it. But you're likely not going to have to keep iterating because most of the questions are designed to be shorter than this at least. So if we keep going, we eventually get to 2.081 and 2.003, which is about 3% error, which is one significant digit correct. So if you want to know how many sig figs you have right, the rule is if the error is below 5% but above 0.5%, then you have one right. So to see that, the next iteration yields these two numbers, which is 0.157%, which gives us 2 sig figs right, we're gonna stop there. You guys should get the idea for this, and yeah, so if you ever need to use a numerical method, Newton's method is on, again, page 60 of the FE reference handbook, and it's very easy, very simple to use, but very versatile as well. Okay, so for the next method, we're going to be doing the secant method. Now, this is not in the FE reference handbook, but it is a stronger, more robust method than Newton's method, just in case Newton's method's not working out and this one clicks a little better for you. So for our next one, it's use secant method to find the root until 2 sig figs are correct. So we got our function here of x cubed plus 5x squared minus 7, and two initial values of x naught of negative 0.01 and x1 0.5. So secant method's pretty similar to Newton's method. So I'll write out the formula here. So there's the secant method equation. So first we need to find x2 since we have our two initial values. So x2 equals, so xi is going to be x1, so we got that for 0.5 minus f of x1, which is 0.5, 0.5 minus negative 0.01 all over f of 0.5 minus f of negative 0.01. So I'm not going to calculate all that out, but you'll get 2.58 going through that. So then we'll keep going and iterating. This time for x3, we'll bring this one down to here, 2.58 minus f of 2.58 times 2.58 minus 0.5, bad 5 there, 5 over f of 2.58 minus f of 0.5. So you plug and chug through there, you'll get 0.738. So I'm going to make a table again to organize our work. It's going to be slightly different than the last one. So for this, we'll have x of I minus 1, x of I plus 1, our error again, and m for our number of sig figs correct. So for the first one we did, x of I minus 1 was this, and 0.5, 2.58 is what we found. And if you find, if you do the same method for finding the error, you'll find that it's about 80%, so that's no good. We have 0 sig figs correct. So this is why it's good to set this up in a table like this. You can kind of follow a pattern. So xi will become xi minus 1, so you can bring that down here. And then x of I plus 1 will become x of I, so bring that down for the next iteration. And then you plug and chug through again, which we did, and we found 0.38. And then we do the error, which ends up being 250%, so awful, terrible, we don't want that. So I'm gonna go ahead and finish up this table. If you want to go ahead and try it yourself, you can pause the video, and if you can make it through the whole iteration to get 2 sig figs correct, which remember is below 0.5% error and above 0.05%. So go ahead and do that, but I'm going to fill this all out and see how you did. Okay, so there's our finished table, and if you made it to that point, great job. So yeah, those are my two numerical methods examples. Likely not going to see secant method on the FE, but it's great practice, and it's it's good to understand the pattern of, you know, how to find these approximations, how to know how many sig figs you got correct. But anyway, I again apologize for not making videos for so long. Hopefully I'll have a more secure, regular schedule now, so I can actually start pumping these out a little more. But hopefully these examples helped, and yeah, see you in the next one.